Ladies and gentlemen, my name's Mike Lockwood. I work at the Space Science and Technology Department at Rutherford Appleton Lab and at the School of Physics and Astronomy, Southampton University. And I'm also proud to say that amongst my previous employers is NASA. And it's a great pleasure to welcome you all to the Royal Society tonight, and a great honour to introduce to you Mike Griffin. But before I do so, I have one thing to ask of all of you, and that is, rather like those terribly nice air hostesses on aeroplanes, can you just check that your mobile phones are all switched off? So if we don't want any, tonight's will be a very interesting and important talk, so we don't want any interruptions. Thank you. Mike Griffin began his duties as the 11th Administrator of NASA in April 2005. And indeed, what duties they are, because he heads the team and manages the resources for the US Vision for Space Exploration program. Before that, he was head of the Space Department at the Applied Physics Laboratory of the Johns Hopkins University. And he also had served as chief engineer and associate administrator for exploration within NASA. As well as being a professor at Johns Hopkins University, he's been a professor at the University of Maryland and George Washington University, where he taught courses in spacecraft design. I seem to remember it was called applied math over there, guidance and navigation, astrodynamics, and introductory courses on aerospace engineering. He's the lead author of a great many technical papers and reports, as well as a seminal textbook called Space Vehicle Design. For these activities, he received NASA's Exceptional Achievement Medal and the American Institute of Aeronautics and Astronautics Space Systems Medal, and the Department of Defense Distinguished Public Service Medal, which is actually the highest award given to a non-government employee. And on top of all that, Mike is a certified flight instructor. Now, yesterday I had the great pleasure of attending a lunch in honor of Professor Stephen Hawking, who I'm delighted is with us tonight as well, when he received the Society's Copley Medal. Mike was there along with 4 astronauts, the crew of the STS-121 flight of the Space Shuttle, who took the Copley Medal with them and returned it safely not only to Earth, but back here to London to be awarded to Professor Hawking. And it struck me that the men and women of STS-121 really were the latest of a long line of explorers, a line that starts with the navigators that explored our oceans and charted them, and continued after a bit of a pause by the polar explorers, and then again after a little pause by the cosmonauts and the astronauts that explored our near-Earth space environment, culminating, of course, in those few visits to our nearest neighbor, the Moon. And now mankind is ready for the next step. And I'm absolutely delighted to see from Mike's abstract for this talk that he sees that next step as part of this history, for it is a long, noble, and distinguished history indeed. So without any further ado, ladies and gentlemen, I'm very pleased to present to you Dr. Mike Griffin.
Good evening, ladies and gentlemen. I am truly honored to have been invited to speak to this august group. The Royal Society has a long and distinguished history of supporting explorers and scientists. And indeed, I think for centuries we have to say that the Royal Society has been the embodiment of science in Western civilization. I'm particularly honored to have Professor Stephen Hawking here tonight. If my wife would, in the world, most like a meeting with Paul McCartney, I am most thrilled by having a chance to meet Professor Hawking, who is, in my line of work, what a rock star might be to other people. In fact, indeed, I would rather be sitting and listening to a lecture by Professor Hawking than giving this talk myself, but that is not the way of it tonight. And in fact, yesterday I had the honor of making a very special presentation of the Society's Copley Medal to Professor Hawking. This medal, the world's oldest award for scientific achievement, flew on Space Shuttle Discovery last summer, as Mike Lockwood just pointed out. It flew, however, more to the point, as part of the personal effects of British-born astronaut Piers Sellers, as a gesture of honor to Professor Hawking. Now, next week, we hope that Space Shuttle Discovery will roar back into space with the STS-116 mission to continue the assembly of the International Space Station. When it does go, another British-born astronaut, Cambridge graduate Nick Patrick, will be aboard. The upcoming missions of the Space Shuttle to finish the space station are among the most difficult and complex that have ever been undertaken. They are more complex than the Apollo missions to the moon. On this mission alone, the crew will add another segment to the space station truss, which is the backbone of the configuration. When it is complete, it will be almost 300 meters long. They will reconfigure the electric power system to incorporate and use the new solar arrays brought up on the last flight, and they will fill and activate the ammonia cooling system for 2 of the truss segments. The exploration and development of the space frontier is truly the most technically challenging endeavor of our generation, and many to follow. But in carrying it forward, we're building on the heroic exploits of our forebears in their own missions of human exploration and scientific discovery. And linking those 2 eras is the purpose of my talk tonight. Now, I have no greater personal hero than former British Prime Minister Winston Churchill, a man whose distinguished paternal ancestors served Britain for centuries, going back to, of course, John Churchill, 1st Duke of Marlborough, widely regarded as possibly the greatest field general that the British have ever produced. Sir Winston, of course, was British, but born of an American mother. And throughout my life, I have admired Churchill's famed incisive wit, his stunning oratorical skills, his steadfastness in support of that in which he believed, even during periods when others did not believe as he did. And above all, the unbreakable rock of his courage. During the darkest days of World War II, as he sought to bolster his countrymen and those everywhere who fought for freedom, Churchill once exclaimed, "We have not journeyed all this way across the centuries, across the oceans, across the mountains, across the prairies, because we are made of sugar candy. Nor will we journey into space and make the solar system our own by being made of sugar candy." The United Kingdom is a truly great nation, a nation whose people and culture have spread across the globe, and whose language has become the world's most common second language, due in no small measure to the support of the Royal Society for its nation's explorers over the centuries. As we consider the migration of human beings out into space, first to the moon and Mars, and then eventually beyond, I think it's interesting to look back and to consider the migration of the human species and its languages and cultures to all of the continents of this planet. Our forebears have left us a history filled with lessons for the future. Some of these lessons are evident in my own land. America's origins do not begin on a specific date, nor do they involve any one particular group of people. In America, we are descendants of pioneers from Spain, Portugal, Holland, Scotland, England, France, Germany, Italy, many other countries. People who migrated over many generations and settled in what is today the United States in search of new riches, new freedoms, and new beginnings. The several peoples of the British Isles were not the first of these many groups, but they were, in the end, the boldest and the most persistent. And so, over many generations, the primary language of the United States came to be English, and our dominant cultural traditions are derived from Great Britain. Thus, while we Americans are quite a mixed bag, in many respects we are your cultural, political, and quite often genetic descendants. One of my own great-grandfathers emigrated from Scotland. Another great-grandfather was Irish. A third great-grandmother was a Hobbs. And my surname indicates the presence of a Welshman, at least somewhere on my family tree. So my hope is that the English language will not only remain in common usage around the world, but will spread throughout the solar system over the course of the next century. As modern-day explorers like NASA astronauts Piers Sellers, Nick Patrick, and their successors carry the British heritage with them into space. That is truly a lasting legacy for a great people. I'm not a historian, but I am mindful of the lessons of history and how we can apply them to the challenges that NASA faces today in space exploration and scientific discovery. The Royal Society was one of the primary benefactors to many great maritime explorers in the 17th and 18th centuries. Today, in many respects, NASA is carrying on that same tradition of combining exploration and scientific discovery that the Royal Society initiated centuries earlier. Indeed, we at NASA are so beholden to the Royal Society and its traditions that 2 space shuttles, Discovery and Endeavour, were named in honor of sailing ships used by James Cook, one of Britain's and history's greatest explorers. And when astronauts Dave Scott and Jim Irwin voyaged to the mountains of the moon on the Apollo 15 mission, their command ship was also named Endeavour. So in drafting my speech for today, I thought it might be insightful to consider the connection between certain lessons from Captain Cook's initial South Pacific voyage on His Majesty's bark Endeavour to the work that we at NASA are carrying out today in exploring the planets, moons, asteroids, and comets of the solar system. Cook's first expedition to the South Pacific, beginning in 1968, was funded jointly by the Royal Society and the British Admiralty. The primary purpose of the voyage was to obtain astronomical observations of the transit of the planet Venus as seen from Earth across the disk of the Sun on Saturday, June 3rd, 1769. This was not that important to the British Admiralty, so the Royal Society was predominantly behind that. But the secondary intent of the voyage was to search the South Pacific for signs of the southern continent, Terra Australis, which had been conjectured to exist by members of the Society at that time. Cook was only 39 at the time, and from my present vantage point, he was clearly far too young to be entrusted with such major responsibilities. What in heaven's name were his superiors thinking? But I digress. If I were speaking to the Royal Astronomical Society, everyone present would understand why the Royal Society was interested in having Cook and a team of scientists observe the 1769 Venus transit, and I could save a few words. But for tonight, with many other specialists probably present, we should probably note that prior to the invention of radar and later the capability to send spacecraft to other planets, it was extremely difficult to determine the actual size of the solar system. It was known, for example, that Jupiter was 5 times farther from the Sun than was the Earth, but the distance in miles was not known and very difficult to determine. However, by using a method first proposed by Royal Society member Sir Edmund Halley, it is possible to use observations of a Venus transit to establish the solar parallax, and from that to establish the size of the astronomical unit, or the AU, and with that to determine the scale of the solar system. Venus transits are one of the rarest of predictable celestial events, typically lasting for only a few hours as seen from any given point on Earth. Between the middle of the 12th century and the middle of the 39th century, they occur in a 243-year cycle with appearances of the transit 8.5 years apart and separated by gaps of over a century. The most recent Venus transit occurred in June of 2004, and the next one will be in December of 2012. After that, we need to wait until 2117 for another. Now, I observed the 2004 event personally, and it is probably not too much to hope that I will see the 2012 event. I expect I shall be missing the one after that. The practical difficulties of making such observations were substantial in the 18th century. First of all, it is necessary to measure quite accurately the entry and exit times at which Venus crosses the limb of the Sun as seen from widely separated points on Earth, as widely as possible, because those points constitute the base of a triangle used to determine the angular parallax of the Sun. So, to begin with, of course, it's necessary to meet the fundamental challenge of merely traveling to various distance points on the globe, and as many as possible, including in Cook's case, the South Seas. This was an enormously difficult prospect for the time. Considered objectively, I really think you have to say that it was fully as difficult, as dangerous or more dangerous, and more time-consuming for Cook and the Endeavour to reach the South Pacific as it will be for the first voyages to reach Mars. My personal opinion is that it was far more difficult given the technology of those times. I believe that this is an important perspective for those who seem to believe somehow that the exploration of space is uniquely different as compared to the exploration of the Earth by Europeans beginning in the 16th century, 15th century. And so this is the first lesson that I think Captain Cook leaves behind for us today. And in fact, we must ask ourselves, are we to quail before multi-year voyages to uncertain destinations when our ancestors did not? Among the many challenges of long sea voyages in the 18th century was, first of all, the basic task of determining one's location. Accurate and consistent timekeeping at widely separated points, which is equivalent to knowing one's longitude, was still a major challenge in 1769 and nearly impossible to do while aboard ship. Today, we take for granted GPS navigation, navigators that receive precise timing signals from satellites with atomic clocks in orbit around the Earth. But back in 1769, Captain Cook did not have the benefit of an accurate chronometer. It was not until his second voyage to the South Pacific a few years later that Cook carried with him the K1, a copy of Harrison's famous H4, the clock that won Harrison the famed longitude prize in 1773. Indeed, modern-day navigators and timekeepers using GPS are, I think, forever indebted to John Harrison and his famous clocks, which, of course, can be seen today at Greenwich Observatory. Captain Cook learned the value of accurate navigation and precise timing in the late 18th century, and the ability to carry out the primary purpose of his mission was only barely possible with the technologies available to his expedition at that time. He didn't have a good map, and in fact, in part, his job was to help make a good map. Modern-day explorers and scientists also know the value of a good map. Data from NASA's Landsat satellites provides the backdrop for maps provided by Google Earth and other online services. We will need a similar navigation infrastructure on the Moon for future explorers and scientists. Scheduled for launch in 2008, NASA's Lunar Reconnaissance Orbiter, with its laser altimeter and other instruments, will provide an accurate global map of the Moon for future explorers. We're still formulating our plans for providing communication and navigation for future lunar explorers, but I can certainly foresee NASA collaborating with other spacefaring nations, like the United Kingdom, in providing such infrastructure. Again, such collaborations have a long and honorable history. In another interesting parallel to space exploration today, the effort to observe the 1769 Venus transit was an early example of international scientific collaboration. I mentioned that it was desirable to view a Venus transit from as many opposing points widely separated as possible. And Cook's expedition to the South Seas and his sighting of the Venus transit from Tahiti, which had only been discovered the year before by English navigator Samuel Wallis, was but one of many similar efforts, with scientists and explorers from Britain, Austria, France, and other countries traveling to Siberia, Norway, Madagascar, and the southern tip of Africa. In fact, Catherine the Great of Russia invited astronomers to observe the transit of Venus from her observatory in St. Petersburg. So, similarly, as of today, NASA has, I think, 58 ongoing space and Earth science missions in which we either lead or take part. And over half of these missions have some form of international collaboration. 2/3 of all of the NASA missions currently under development incorporate international partnerships in one form or another. And of course, NASA's premier human spaceflight program today, the development of the International Space Station, is an effort that involves some 15 other nations. So, like the collaboration for the Venus transit, NASA's partnerships in space exploration and scientific discovery take many forms with various levels of contribution. We do not always lead. For example, we are contributing 2 payloads to India's Chandrayaan-1 mission to the Moon, planned to be launched next year. For the Calypso mission launched earlier this year, we've developed a LiDAR payload, and the French Space Agency integrated that payload to their satellite bus, and NASA launched it. The British National Space Centre provided a high-resolution atmospheric sounding payload to the Aura Earth Science mission that we launched 2 years ago, and provided 2 instruments to the Stereo mission, which we launched last month. In the next decade, the European Space Agency will launch the James Webb Space Telescope, which will largely be built in the United States, but which will carry international instruments on board. It will be launched on an Ariane 5 rocket. One of the more unusual aspects of Cook's first expedition is that few members of the crew of Endeavour contracted scurvy, a disease, of course, now known to result from a lack of vitamin C. By the mid-1700s, it was known that a poor diet caused scurvy, but the specific cause was not known. Captain Cook led by example and motivated his sailors into eating vitamin C-rich but not very tasty sauerkraut by being the first to eat it himself during his meals. Those who refused to eat it were whipped until they did eat it. It's worth noting that by these means and others, Captain Cook was praised upon his return for the survival rate and the health of his crew. Out of the 94 people who started, and the 8 additional sailors picked up at various ports along the way, Cook lost only 38 men to things such as disease, being swept overboard while rounding Cape Horn, and other misadventures. This was considered an exemplary record for the day. And we think we have it difficult in a traffic jam. Now, while today's space station crew members don't get scurvy, they do face other medical issues. For example, muscle and bone density loss due to a lack of tension on the human body in zero-G is now well known in space biomedical circles. While there is a significant degree of variability between station crew members in the amount of bone loss, the average density lost in the spine and the hip areas is about 1% per month. This rate of bone loss is about 10 times worse than those who suffer from osteoporosis here on Earth, which of course all of us, I think, are aware can be a crippling disease for those of us who age. Thus, like sailors of the 18th century, our astronauts on the space station or in future missions to Mars face significant medical hazards in the form of bone fractures because of depleted calcium levels and kidney stones from excessive calcium levels that could jeopardize their health and their mission. The equivalent of sauerkraut for modern-day astronauts so far is the unpleasant but necessary nutrition and exercise regimen to create muscle tension and mitigate bone loss. But these are at best stopgaps, incomplete and unsatisfactory. Whatever therapy we finally develop to control bone loss in astronauts will have application immediately to sufferers of osteoporosis everywhere. Astronauts, in fact, have already conducted clinical trials for new osteoporosis drugs on board space station, and I'm sure we'll be doing more of it. We have much to learn, and in learning, we will create knowledge that can help people everywhere. For exploration beyond low Earth orbit, radiation is another hazard to be dealt with. And at this point, I have to again quote Churchill, who famously said that the grammatical prohibition against ending a sentence with a preposition is, quote, an inconvenience up with which I shall not put. So, to deal with this, the Earth's atmosphere, and especially its magnetic field, shields us on the ground from nearly all of the effects of solar flares and galactic cosmic rays, even to the extent of providing quite substantial protection for low-orbiting astronauts. However, despite this shielding effect, periodic and highly intense solar storms do wreak havoc with power grids on Earth and scientific satellites in high orbit. And on several occasions, space station astronauts have hunkered down in heavily shielded areas of the station when solar flares or coronal mass ejections were predicted to be heading toward Earth. Now, as we venture farther away from Earth, the need to protect astronauts from this energetic particle radiation becomes more critical. For example, back in August of '72, halfway between the Apollo 16 and Apollo 17 missions to the Moon, until that time, most powerful solar flare ever recorded occurred that would have seriously endangered, if not killed outright, our astronauts had they been en route to the Moon or on the lunar surface at that time. An even larger sequence of solar events occurred in the fall of 2003. We must provide our astronauts with both warning systems and effective safeguards to deal with that hazard. Looking through the eyes of multiple spacecraft over the last 5 decades, we've seen in truth that the planets of the solar system are embedded in the heliosphere, the exotic outer atmosphere of the sun, which emanates from and is shaped by the sun's intense magnetic field. This heliosphere is analogous in many ways to the winds and currents of the Pacific Ocean that propelled Cook's Endeavour, but which also endangered the vessel and crew during periodic storms. Thus, we must build our ships in ways that shield the astronauts and instruments inside, and we must provide timely warnings and predictions of solar storms, just as we do now with weather forecasts here on Earth. Space weather monitoring and forecasts need to be extended beyond low Earth orbit, out into cislunar space, and eventually beyond when we begin missions to Mars. This effort to safeguard both our planet and our astronauts from solar storms must be an international endeavor, just like the information from an international network of weather satellites and forecast centers today is shared around the world. We will benefit all mankind in the process by planning these heliophysics missions together. I mentioned earlier the STEREO mission, which consists of 2 satellites intended to provide 3D images of the coronal mass ejections from the sun and other solar activity and its effects on Earth's magnetosphere. The STEREO mission has, as I said, several international partners. Two instruments came from Britain, and will provide warnings that are useful around the world. This is additional evidence that NASA simply cannot go it alone, doing everything that needs to be done. We really do need to work together. Scientific discoveries are sometimes elusive, but we must persevere. As things turned out, despite the best efforts of Captain Cook and his men and the other international collaborators in measuring the Venus transit, the separate measurements taken by the various scientific expeditions on board the Endeavour at Point Venus in Tahiti and other places around the globe varied greatly and ultimately were inconclusive. That was the last transit until 1874, the 1761 transit measurements not having been proven to be all that successful either. And it was quite a while before a successful conclusion, in fact, was obtained. It turned out to be very difficult to measure the precise limb crossing times for Venus against the bright solar background. A now notorious observational surprise, the so-called black drop effect, smears the image of Venus precisely as it is tangential to the solar limb, which of course is exactly the time one wishes to measure. This is essentially the same effect that you can observe by holding up, say, 2 thumbs against a bright light and moving them close together, and just before they touch you will see a little dark interference fringe between the 2 thumbs, and that is another manifestation of the black drop effect and smears such observations. So none of the observations from the 1769 transit, whether from Cook's team or others, were very good. In the end, it had to wait until the transit could be captured by photographic images of Venus crossing the sun, and the proper inferences drawn as to when the moment of tangency was reached. And so the astronomical unit was not, in fact, accurately determined for over a century until the 1880s, when American astronomer Simon Newcomb published a value of about 149.6 million kilometers using data from the 1874 and 1882 transits, as well as corrected data from the earlier 2 transits. And that was within about 30, I think, million kilometers of the correct value. Today, of course, the value of the astronomical unit is known to about 30 meters as a function of radar observations that have been made. So we've substantially improved those values. So we must recognize that while the mysteries of the universe may not elude Professor Hawking, these mysteries do, in fact, frustrate the rest of us who are mere mortals. So we must be especially resolute in our convictions, and despite setbacks, we must recognize that progress through human exploration and scientific discovery is a goal that is worthy of the costs and the risks of the enterprise. Again, to echo Churchill, we're not made of sugar candy. But the disappointment encountered by Cook's expedition yields, in fact, another lesson for space mission planners today. Cook's voyage was not judged, nor intended to be judged, solely on its ability to obtain accurate measurements of the transit of Venus. Indeed, Cook's own logs devote relatively little space to the frustrations of the Venus measurement, and quite a lot of space on the incredibly new and different cultures that he found in Tahiti and the new lands that he found. So Cook is today remembered above all else for his discovery, the first by European voyagers, of Australia and New Zealand, and who today would label Cook's first South Pacific voyage a failure because the measurements of the Venus transit were inconclusive. We must remember this and similar experiences when our future space missions encounter difficulties, and we must plan them so that they are not hostage to a single piece of fortune as a measure of their overall success. There's another lesson to be gained by looking back across the centuries at the voyages of Endeavour. Although Captain Cook no doubt considered his vessel to be the apotheosis of shipbuilding arts, as they were then known, at least I hope he did, we can see in retrospect that the Endeavour occupies but one point on a long curve of ever-increasing maritime capability, beginning for Europeans with the Viking longships and culminating in today's supertankers. One must realize that there will be a similar performance curve for space systems, and that, humbly, we today have not yet advanced very far along it. We are at the dawn of the space age. Metaphorically, we are sending out Viking longships, not supertankers. We have a long, long way to go to get to supertankers. We must constantly, therefore, question our assumptions as to how we build and operate our spacecraft and launch vehicles, because we have a lot yet left to learn. Each generation of our spaceships must be greater than the last. And so, for example, the space shuttle system, including the orbiter, the solid rockets, the external tank, requires almost 2 million labor hours to prepare for launch. We've analyzed this processing labor, as well as that required for other launch vehicles, both foreign and domestic, manned and unmanned. And using these other systems as a guide, I believe, and have set forth a goal, that NASA's next generation crew launch vehicle, the Ares 1, we are naming it, should require an order of magnitude fewer labor hours to process than the space shuttle. The savings in launch vehicle operating costs can then be applied to future systems and bolder missions. With the retirement of the space shuttle in 2010 and development beginning for NASA's new Orion crew exploration vehicle and Ares 1 crew launch vehicle, we're beginning to lay the keel on the next generation of spaceships. So now's the time to question the assumptions and technical dogmas that lie behind them. Reflecting upon his journeys, Captain Cook once said, "I had the ambition not only to go farther than any man had ever been before, but as far as it was possible for a man to go." While some people might ridicule such bold ambition, I think that it reflects the determination that is innate in all of us to push the limits of our technological capabilities and human faculties. However, I will express a certain lament to those sympathetic and like-minded members of the Royal Society who are, with me, concerned that our broader society today often seems to suffer from a lack of imagination in grasping the importance of the challenge before us. One of the minor misfortunes of modern life in our nation's cities today is that our nighttime lighting has drowned out our view of the rich constellation of stars and planets in the night sky, and we find other idle pursuits, such as television, to occupy our time. I might have added rock stars. Thus, we today do not look up nearly as often to marvel at the beauty and mystery of the night sky as did our ancestors, who imagined the stars to represent constellations of mythological beasts and legends, while the planets represented gods. I'm personally happy that we've progressed beyond that. To me, the view of Hadley Rill from a camera mounted on the Apollo lunar rover was a lot more exciting than imagining the moon to be the huntress Diana. But there's no question that we modern folk are less concerned with the heavens than were our ancestors. But if we do the right things, maybe we can alter this perspective. The British Royal Astronomical Society recently released a report advocating the expansion of British involvement in human space exploration. I hope that report receives sober consideration in the policy circles of the United Kingdom. And I hope that I can count on you to be one of the international partners who, with the United States, will work to develop the first permanent lunar outpost in the next decade. And last month I made the decision, which was a culmination of 18 months of work by NASA engineers and scientists, to conclude that we could effectively and safely conduct a space shuttle servicing mission to the Hubble Space Telescope to extend the life and capabilities of this great observatory. I've been struck by the tremendously positive response this decision has received, and by the way that people from all over the world have been awed and inspired by Hubble pictures revealing a few of the secrets of our universe. Hubble provides glimpses into the universe that are far, far beyond the scale of the astronomical unit, which was the objective for Cook's first voyage. The view of that universe provided by Hubble uplifts us. It gives us a measure of hope. It was the same when the first man flew in space. It was the same when the first man set foot upon the moon. We see a little of it each time a space shuttle crew returns from yet another mission in the sequence to assemble the International Space Station. It's quite possibly the greatest construction project in the history of mankind. We will see it again at its peak when the first astronaut places her boot on the surface of Mars. The human species was not crafted solely for safe places and prosaic times. We are, each of us, descended from people who left their homeland in search of what lay beyond. Today, what lies beyond is space. And so I will quote Professor Hawking: "To confine our attention to terrestrial matters would be to limit the human spirit." I believe with all my heart that with the exploration of space we are embarked upon the boldest human adventure yet conceived. We are limited only by our imagination, our ambition, our ingenuity, our persistence, and our leadership. But we have not journeyed all this way across the centuries, across the oceans, across the mountains, across the prairies, because we are made of sugar candy. Thank you.
That was excellent.
Thank you.
You like the questions?
Sure, plenty of time. I was asked to speak for not more than 40 minutes and leave 20 for questions, and I'm so pleased I've done exactly that.
So is your chairman.
The floor is yours.
Thank you, Mike. That was a talk of great insight. And it shows us that Henry Ford was wrong. We really can learn from history. Now, if you'd like to ask a question, would you please stand up and somebody bring you a microphone? So we'll start with the gentleman over there.
And I think
if you just wait for the microphone to come.
And I think they wanted to line up two at a time so that they could help the AV people.
Okay.
Dr. Griffin, Dr. Griffin, there were reports in the media today of your meeting with the new science minister yesterday when you were said to have invited the UK to play a greater role in the exploration of the moon when you go back as part of President Bush's vision of space exploration. I just wanted to know, did that offer extend to training British astronauts?
Well, I'm sure you will be shocked, very shocked, to know that sometimes the London tabloids don't quite get everything right. The minister and I had an excellent meeting, and I did point out that the U.S. Strategic plan for NASA today, the vision for space exploration, which, by the way, now is the vision of the U.S. Congress, not just of the President, because it has been voted into law, that it is intended to be international in scope, and that I personally would regret it when we return to the moon if we cannot return to the moon in company with our closest ally. And so, yes, the invitation absolutely is there for the UK to join us in those journeys. The level and scope and nature of that participation, of course, will be up to the UK. We are looking for volunteers, not conscripts. And I hope that that level of participation would go so far as to include astronauts. And of course, if it does, and that is a choice that Great Britain must finally make, if it does, then of course we will participate in training them. Another question.
Really following on from that, as the current policy of the UK government is not to support human spaceflight, it means that not only don't we have British astronauts, but we don't have scientists being able to fly their experiments on the International Space Station. And one of the reasons given for this is that it is, quote, believed that robotic missions offer better value for money. Now, I'm sure that that's not a value that you subscribe to, but my question would be then, what would you say are the best arguments we can put back to the UK government to convince them to change their minds on this matter?
That's an excellent question, one, as you well know, that has been debated for 50 years since the dawn of the space age, and probably will be debated long after you and I are dead. Let me offer a couple comments since you've asked. Actually, I would, in some cases, say that robotic spacecraft offer better value than human explorers. That absolutely is the case for some missions. A human operator present on board the Hubble would do nothing but jitter up the photography. Hubble does just fine on its own, except that every 5 years it needs some new instruments and some technology upgrades. I can't think of a better synergy between human exploration and scientific exploration. My own view is that this is not an either-or proposition. It is a spectrum. In fact, it is whoever it was that said all generalizations are wrong, including this one, was a genius. Such generalizations just seem to me to be nearly always wrong. There is a spectrum. On one hand, there are activities which are best carried out for us by our robots. And then there are other activities, principally among them discovering what activities we should ask our robots to do that are best carried out by human beings. And the proper way, in my view, to think of this is that it is a synergy between us and our tools. And then there is a meeting in the middle where there are things which can only be done by humans working in combination with our robots. In the end, I think we should recognize that man is, if nothing else, a tool-making animal, and that scientific satellites that are put there to serve us, whether it is to observe the weather, to supply navigation signals, or to measure the atmosphere of Titan with a probe on the way down to the surface, these are nothing but the most advanced versions of our tools which we have yet conceived. Now, the human without tools will die in almost all climates on the Earth. We could not survive in Great Britain. We could not survive in America. There are very few places on the Earth that we can survive naked and unaided. This is not one of them. We are wedded to our tools and always will be. It is what makes us human. The exploration of space involves certainly new and different tools, but to say that somehow they are different in concept from the tools that the then British pilgrims used to help survive in the harsh Massachusetts climate, to say that it's somehow different in concept is, I think, to miss the point.
Dr. Griffin, you mentioned about your hope that English would become the lingua franca of the solar system.
Makes it easier for me.
But I wanted to ask you this. You spoke also about the collaboration, the international collaboration involved in the Cook voyages, and how that's mirrored in the space programs today. But another reading of history could be that, in fact, a lot of what drove the early exploration was a competition for real estate and a competition between nations. Is there a danger in the potential for space exploration that you've spoken about today, that we could see a new space race, and in fact a small possibility perhaps that the language of the solar system could in fact be Chinese or something?
Well, there's again several questions there and an opportunity to make some comments. First of all, of course we humans both collaborate and compete, and by the way, Cook's expedition that I know of it may have had others on board, but I think it was British. What I was talking about as a collaboration was the attempts to measure the transit of Venus. That was the measurements of the transit were the international collaboration, but moving beyond that, humans both collaborate and compete to our benefit. It's another one of those spectra where either end, adherence only to either end is, I think, wrong. When we compete, we push each other on and advance each other. The best competitor I had growing up playing golf was my brother. He started sooner than I did, and for at least a couple of years, my greatest ambition was to beat him. Now, I wanted to beat him, not kill him. So as long as we are competing among nations and not firing guns at each other or other nasty things, I think that's healthy and useful. In the long run, of course, we seek to exploit the resources of the solar system for the benefit of mankind. There are plenty of them out there. I don't see that this needs to reach the status of a range war, as we had in some of the western part of my country. I don't think we need to go that far to say that we can benefit by both working with other nations and we can benefit by competing with them. Now, what will become the lingua franca of the solar system 1,000 years from now? I don't know. I've expressed my hope that it will be English. But as I pointed out in my speech, these things are only really determinable afterward. The British peoples were not the first peoples to explore North America. They were merely the most persistent. We know today who the first people were to land on the moon. We don't know whether or not the United States will ultimately prove, and its allies and partners will ultimately prove to be the most persistent. I hope that we will, but we don't know it.
Yeah. Gentleman in the middle.
Good evening. Before I ask my question, if I just, forgive me if I just say it's exciting to have an astro administrator who sees a destiny for us among space and doing more than just science and living there and working there for our economic benefit. The question I'd like to ask is, some have criticized the architecture for the return to the moon on the grounds that it is very similar to the Apollo program. And while I'm not sure that those criticisms are entirely valid, what reassurance, and I realize this is probably outside the scope of the architecture as currently designed, but what reassurance can you give that the missions will not simply be a repeating series of Apollos, perhaps building a lunar base, but not in the end contributing to a permanent human presence for the future in space?
There's two questions there, and let me answer the second one first. The question, while quite natural, contains an assumption that wasn't handed down on stone tablets by God, all right? And that assumption is that the Apollo expeditions were dead-ended and you know, flags and footprints is the common theme, and so you're looking for me to assure you that that won't happen again. First of all, the Apollo missions contributed most of what we know today about the origins of the moon. So it can hardly be said, in fact, many have said that scientists hijacked the Apollo missions, as the last three were almost exclusively devoted to lunar science and ultimately geology, which is the study of how the Earth came into being and was formed. So the Apollo missions were not merely stunts. They were not merely test flights. Sure, the first one was a test flight. It could hardly be otherwise. But by the time the last 3 or 4 flew, they were intended to be scientific expeditions. If the Apollo missions seem to have been dead-ended, even despite my comments, if they seem to have been dead-ended, then frankly, that was the result, in my opinion, of a poor set of policy choices by my government almost 2 generations ago. I decried those policy choices as a young engineer, and I have continued in that vein for 35 years. My views were, in fact, not particularly popular in American space circles until fairly recently, and so now, all of a sudden, I've become smart. It's amazing how quickly that happened. In the wake of our loss of Space Shuttle Columbia possibly the most significant aspect of that whole failure investigation by Admiral Gaiman and his board, the most significant thing they did as a legacy to the Columbia crew was to point out that with the technology we human beings have today, for the foreseeable future, 2 or 3 generations, I mean, I can't see any farther than that, space exploration is going to be expensive, it's going to be difficult, it's going to be dangerous. But it's important. It is strategic, the report said. And so if we're going to do it, the goals ought to be worthy of something which is expensive, difficult, and dangerous. And oh, by the way, flying the space shuttle to the space station is not such a goal. It is necessary to go beyond. The United States developed a transportation system capable of going to the moon and then discarded it. An act that I personally think history will record as a monumental waste. Not that there was anything in any way bad to do about developing a space station. It's again a matter of going to extremes. We elected after the Apollo era to say that we will only be in Earth orbit. I think it would be equally wrong to say that we will only go to the moon or only to Mars and we have no interest in Earth orbit. That's silly. The extremes are silly. So it is our political decisions, not our hardware, that renders our mission choices either dead-ended or open-ended. Had we continued to use the 1960s hardware as our Russian colleagues have done for several decades until and unless it became possible to upgrade them, we would not today think of the Apollo missions as dead-ended because we would have had several dozen of them and we would have decided whether it made sense to establish an Antarctic-style outpost on the moon or not, based on the data that we gathered. So dead-ended is versus open-ended is a political choice, not an engineering choice. It is not linked to the hardware. Now, you commented on the fact that the transportation architecture we have has some similarities to Apollo, and it has quite a few differences. In fact, the major similarity is in the nature of the Earth return vehicle, the command module. I would point out that that was dictated largely by the physics of atmospheric entry at 11 kilometers per second, which is not trivial, nor is, as is the development of a database for such a vehicle, not trivial. Now, we could have developed another aerodynamic shape, and I'm sure it would have worked just fine, but we had a known aerodynamic shape that also works fine and for which we largely have an extant database. Why would I go to a lot of trouble to develop a different one? I am an engineer, not a theologian. Engineers, good engineers, in my opinion, use what they have that works and use that to build upon something more. And in fact, our excitement and our interest in the lunar and Mars ventures to come and beyond should not be the excitement engendered by the transportation system. The interest ought to be in the destination. And so I'm actually rather proud of the fact that our lunar transportation architecture, which we in the United States find it necessary to redevelop because we threw the first one away, I'm actually rather proud that that transportation architecture invents as little as possible rather than inventing as much as possible. The interest is in the destination, not in the railroad, my view.
We have one more question at the front here, if we have time. It's coming. Just hold on. There we go. And
cheers.
Can you stand for the
Sure.
camera?
Yes. Ian Buxton, my name is. Would you say that in the very long term, say centuries hence, I know it's difficult to make that kind of very long-range prediction, humanity needs to develop a manufacturing capacity on the moon so it can sort of produce metal components and actually assemble maybe in lunar orbit, because the gravitational lift from Earth is very expensive. You have to throw away about 90% plus of your vehicle. Obviously, if you can have a bigger payload in a lower gravitational field, that's better, but we need to actually create a beachhead, as it were, on the moon. Would you agree with that proposition?
I have absolutely no doubt that our descendants will utilize, capture, utilize, refine the resources of the solar system and utilize it to make manufactured objects in space, absolutely as we do here. I mean, to imagine otherwise, I think, is inconceivable. When European pioneers settled in America, they very quickly abandoned the practice of trying to bring everything they needed with them and learned as quickly as possible to live off the land. As quickly as possible was not sufficient to save 50% of the pilgrims from dying the first winter, but those who remained, I assure you, knew how to live off the land of New England. And our successors will find it so in the solar system.
Okay. Well, thank you, ladies and gentlemen, for A, your interest, and B, your excellent questions. I think we should thank Dr. Griffin for a talk of remarkable insight and wisdom, as well as an inspirational talk. So if we give our appreciation in the normal way. Thank you.
Again, it was a real honor to be here with you tonight, an honor I very much appreciate. Thank you.